And just to say the type of work that we've done. So, um, Michael and I, for those that aren't familiar, before we started collaborating with Willie, we spent like years on a researching from like 2010 to 2014. We started looking into climate change because we started to see some scientific problems, and so we found that there's a lot of different papers, or we decided we could write these up as scientific papers, but they were all quite long, and they we saw that they were undermining key paradigms. And we said this is not it's not going to get published in a standard peer reviewed journal. And we said, let's just set up a new open peer review journal and put up all of our analysis, these working papers, and let everyone look at it and let the public view it rather than waiting for
A, a lot of people, when we set up the open peer reviewed journals, which allowed anybody to come in and make comments on our work, they
yeah,
said that it would be inundated with rubbish. But it
yeah,
turned out that wasn't the case at all.
yeah.
Uh, we found we had very interesting debates with people going on.
Well, it's a new paradigm for science. I mean, I wouldn't even call it new. In fact, in the past, it's always open. I mean, there was a lot of secrecy.
But,
Now in peer review, they're becoming
but
a bit of a problem. But
what we
anyway,
did,
let's move on and talk about the
Well,
main.
I just to give the background
Sorry
because
that I'm rushing because of
yeah,
the time constraint.
yeah, no, but we'll give a bit of the background and to explain these papers. We would recommend that you read them. Anybody that's interested in them, they're more detailed. You can still
well,
find
I
them.
think, Ronan, just what we should point out here is these papers that we put in this open peer review journal didn't go through the standard peer review process.
Yes,
Uh, so we call them working papers
yes,
uh, for that. But since then, we've had 20, 30 peer reviewed papers going through the standard peer review process. So,
yes.
what we're going to be discussing in a few minutes are actual papers that have gone through the standard peer review
By the
process.
Yes,
way,
and
I just
it's
speak from my own point of view. As again, you
yeah.
guys might see already, three of us always disagree on things. I can tell you, as an independent scientist that practiced this science for a long time, this paper is groundbreaking. Each of every one of them is crazy good. I mean, it really does put us down a little bit, calm down about how much we don't know. And Ronan and Michael are truly unique individual scientists that is couldn't care less about how the world thinks. And then they really think very quietly about all this topic, examine in thorough detail. This is why each of the paper is really thick. I mean, I apologize in advance again, but it's beautiful work, and please read them when you have a chance. But hopefully, we will inspire you to read some of this stuff. But we are continue to try to get it out there in the public sphere in a peer review sense, so that we can publish it in a standard way like normal people. But even this is more than sufficient. I would say that when I try to review some of this paper, I mean, it's clearly well done. Well done in terms of every aspect of it, the analysis, the context, the review of the subject. Each of them are highly knowledgeable and add that actually not add a bit of knowledge. For this particular work on the balloon, is truly unique. I think it had a change of paradigm potential. So let's move
Th-
on. It's
Thank,
beautiful piece of,
thank
beautiful
you for
work.
those kind words, and then we'll go on. So I'm just going to.
Ronan didn't pay me. Just kidding.
Yes. I'll just describe one of the bits. We just got to focus on one aspect, but you can read the papers for other ones.
Yeah, and many other
This one
papers
we're
of different
looking at
subjects.
weather balloons. So the just a bit of terminology because you'll see this. The there you'll hear people saying radio sondes, and what they mean is a weather balloon. So a sonde comes from the French for a sounding. So if you are doing a measurement down into the ocean, you would do a sounding going down into the ocean. And so then when people started using weather balloons, they said, well, it's like throwing a thermometer up into the air and it goes up. So they called it a sonde. And that was a balloon sonde. And then in the old days, they used to just physically they put a little note on it because when the balloon bursts, it could last miles and miles away. So they put a note: if you return this to the Met Office, we'll give you a finder's fee. I don't know the equivalent of what, probably like 50, $100 or something. I don't know, or something. It was worth doing enough to make it worthwhile. But then in the 30s, they started getting these radio transmitters. So they would be able to use that. So now they're called radio sondes. And what they do is they record temperature, pressure, humidity, wind speed. And there's about 2,000 stations around the world that launch at least one a day and up to four a day. And they can reach up to 30, 35 kilometers. And so we won't get into too much details here, but just to give you the picture, um, when you see a shooting star, it's in the meteor zone. Um, the ozone layer is in the stratosphere, and the what we're used to is the troposphere. And this is defined. Michael will talk about this later, but the troposphere is as you go up in the atmosphere, it gets colder, and that's why when you climb up a mountain, it gets colder as you go up. And so the temperatures get colder with height. But when they first started looking at weather balloons reaching up further, they noticed that the temperature stopped getting colder with height, and they said, "Oh, that's the tropopause." And then above that, they found that they started getting um, hotter with height, and they call that region the stratosphere. And then it goes through other stuff, but the balloons typically burst around here.
35
So,
kilometers. Yeah. Okay.
so now if anybody wants to look at this stuff for themselves, we are mostly using NOAA's IGRA data set. Um, we That's the best for doing large analysis. But like if you're just kind of want to just download a balloon for yourself and look at it, and
Yeah,
uh,
station in your cities. Yeah.
yeah, there is. I just Google University of Wyoming atmospheric soundings, and you can download the weather balloons for yesterday, today, and Michael and I gave us a presentation in 2019 in Tucson, Arizona, at the Doctors for Disaster Preparedness. And so, in preparation for that, these are some slides from there, and we decided to look at Tucson. And so you get this
Well,
is
before you go on, this was only an example, but we actually analysed over 20 million
yeah,
radio sound
Oh yeah. Oh yeah.
from all over the world for the last 70 years.
yeah,
So
yeah. Mainly since the 50s, the resolution, but there are some that go back to 1909 and 10. But they record pressure, height, temperature, dew point, depression, relative humidity, and humidity. Let's not get too much into the details.
Yeah.
The
Yeah.
key bit
Move.
for this is they record pressure and temperature, and so that's relevant. I got to hand over to Michael soon, but I just to say, so if you've done if you did like chemistry, or yeah, if you did chemistry in high school or in university, you might have heard of the ideal
or
gas law,
physics.
or maybe engineer, a lot of things. If you may have heard of the ideal gas law, and this is a well-known thing called so it says PV equals nRT. So the pressure
Volume.
times volume is equal to the number of
Oh, mole of
moles
gas.
times the or, which is 8.314, it's a constant,
I
times the
think that's
temperature.
constant.
And these all have to be in what are called SI units. So instead of Celsius or Fahrenheit, you have to convert the temperature into Kelvin, the pressure in pascals, volume in cubic meters. And what is a mole? A mole is a way of describing the number of molecules in a volume of gas,
Okay.
and it's one
Well,
mole is
specifically, at standard temperature and pressure, it's the number of molecules in 22 0.4 liters
Mhm.
Yes, yeah, of a gas,
of
and
a
that
gas.
works out as this number, which is this big one here.
The great avocado.
Yeah, yeah, called this Avogadro's number. It's basically 6 with 23 zeros after it. That's a lot of zeros. Now, the significance of this is that this Michael had this realization when he was looking at the weather balloons that if you actually take this equation, you can, using a bit of basic maths, you can rearrange this. So you can get, if you n divided by v is equal to p divided by rt, and that's significant because r is a constant, and the weather balloon measures at each point. It measures the temperature and the pressure. So that means any point in the atmosphere, if you have the pressure and temperature, you can put this into the formula. You can calculate N divided by V, which is the number of moles of gas per cubic meter. And it
Unit
called,
volume.
this is the molar density, moles per cubic meter.
This is
P.
truly one of those light bulb moments, even though the formula has been seen centuries.
Yeah,
And
yeah.
Michael came along and then come up with something. You will see the application, which is really the remarkable in terms of changing the paradigm of how we should understand
Yeah. So
everything, how it should work.
Michael, maybe
More than
I'll
20
hand
minutes.
this.
I got 20 minutes.
Maybe I'll hand this over
No,
to
I
you.
don't even have 20 minutes.
Yeah. Okay.
So, okay, just summarizing here then what Ronan was saying. What you can see is this is the ideal gas law. Now, I should point out when all the work was being done to determine this law, it was all done on air because it was the only gas at the time. And so air under normal circumstances behaves like an ideal gas because that's how the formula was arrived at using air. But this is the way that it's normally put, and this is the energy form. So basically, what the ideal gas law says is that the work energy, which is PV, which is measured in joules, is equal to the number of moles times a constant times the temperature.
The thermal energy.
Both of these units are in joules, but as with any, so basically, this is called the equation of state of the ideal gas. And an equation of state is an equation that represents all of the variables, the standard variables for, say, a gas. And so you have the pressure, the temperature, and the volume, and the number of moles. But most people are preoccupied with the energy form of it. But by just rearranging this here, just in other words, if you divide the n by v and bring the p over to that side, you get this. It's still the exact same equation of state, but it's put in a different form. But now, when you're looking at moles or at the units are molar density, moles per cubic meter. And a lot of people are preoccupied with the energy representation, but the molar density turns out to be even more interesting.
So,
Um,
by the way, Willie, I know Willie has to leave in a few minutes. So if he does need
I will
to,
read
we
through
keep
this.
going.
Let's
We
move
keep
on. I
going
think
to
you
wrap
can do
this
it,
up.
Michael. Just, yeah, because a
But
lot of these let people study the thing. Yeah.
yeah,
Okay,
yeah.
so this is what's interesting is that if you plot the molar density versus the pressure, you get
So the
these.
ground is at the green bit,
Yes, and this
and
is
then
going up through the atmosphere. So as you go up through the atmosphere, the pressure gets less and less. But molar density behaves in a linear way until you hit the tropopause, and then it changes its behavior.
you want it.
Um,
You want
I
it. So
I'll go on.
yeah.
So what you're looking at here is this straight line here is what we would expect for the ideal gas. And everybody thought that that would continue like that. Most people still do think that that would continue like that out into space.
Anybody that thinks on this, rather, sorry to interrupt,
Right.
but
Uh,
most people haven't looked at this, or nobody has plotted molar density before
Now,
against.
the thing is, down at this level here, this region is called the boundary layer. This deviation here from the straight line that you would expect is due to water vapor, and water
Yeah.
vapor condenses out, so
Phase
that
change, yeah.
gives a non-ideal level to it. But I just go on a bit
Yeah.
further. So what you look at here is if you find now this is just for one radio sound on this particular day at that particular time. But it holds true for all 20 million radio songs. It's
Oh,
just the position.
universal.
Yes, it's a universal rule. But you can see that this straight line above the tropopause is different than the straight line below the tropopause. It's still behaving like an ideal gas, but a different type of ideal gas. And so can you run? So, okay, let me go
Yeah.
back a second.
Yeah.
Let's run this.
So, this point here, where these two straight lines cross, we have identified, and I'll talk about that in a few minutes. We've identified this as a location for the tropopause. And so, what we did was for Tucson, because we were given the talk in Tucson, we took the entire previous year and we plotted where the tropopause occurred for each of the things. So, about every 12 hours, you'll get a new slide. So, Ronan, if you
Yeah,
can,
okay. Let me put this on the video here,
yeah.
and then we can start. So on the left hand side here
It's the
is
regular unit. Yeah.
standard plot that you'd see temperature versus pressure. Sometimes people will plot temperature versus height, but pressure we find is more relevant. And so this is the ground. This is the where the balloon bursts. Each of these gray dots is a measurement that was made by the balloon.
You
That's the
sample the
date.
air as you ascend.
Yeah, I'm explaining this now. This is maybe we'll go through it twice.
I
The
think just
first
run it.
time First time you can look at, you can see the way everyone else has been looking at it till now, which is looking at the temperature, and it's kind of all over the place. You can see this bit they call the tropopause because the temperature doesn't decrease with height, with pressure, and then the stratosphere. But then on the right hand side, we look and you see the molar density, and you see it's two straight lines, but they have a different slope, as Micah was saying. So I got to go through this one time, and we'll show just maybe like you can go back and watch it, but look at one panel, and then we'll go back at when it's finished, and you can watch the other panel after Michael's talked about it.
So what you'll notice here is that the tropopause moves up and down on an hourly basis, on a 12-hour basis. And
Hello,
it
Yeah,
can
dynamical meteorology.
yeah. So we're up to April to May. So if you're just listening, it's worth viewing this when you get a chance to go back and rewatch this.
Yeah, so you
Um,
can convince yourself that this is a real phenomenon that is uncovered by Michael's new metrics.
we just did this for Tucson. You can check it for anywhere. Only
Any
difference
station. Yeah,
The only difference is if it's a monsoon weather
right.
or if you're in the poles in an Arctic or Antarctic in the winter, there are differences which we discuss in the
Yeah, those
paper.
are the inversion layer because the boundary layer
Yeah,
goes way up. Yeah.
but pretty much everywhere you can do it. Now, Michael, did you want to just have a comment, maybe just for people to look at when I show this again? I think.
Okay, so two things that I point out is that sorry, I will just
No,
I'll just,
like I just describe the thing. Yeah, if you just describe
what
it,
I
I'll
was
say it
going
again,
to
and then
say
I'll hand
is
it back to you.
if you look down at the bottom, you'll see the line wiggling back and forth, and that's due to water either raining or not raining.
Right.
So that's just something you might be
And
interested
then
in looking.
also notice, I would say also notice as Michael said, the line, this dashed line, the horizontal line represents the tropopause, and it moves up and down quite a
Actually,
bit.
quite a bit. Another thing is the magnitude. Just look at the weather. Yeah, the serious question about this meteorology is basically what is climate, what is weather, right?
Yeah, so we're just looking at it again, maybe focusing on whichever panel you didn't look at before. And you notice that the two things are plotting the same. These are the same measurements. The only difference here, this is kind of the temperature one is kind of all over the place. Um, that's what people are used to. Whereas here is pretty much two straight lines, plotting in terms of molar density.
Over the
Uh,
few years,
is
yeah, and
more
everywhere is the same.
fundamental
Yep.
it's a more fundamental understanding than plotting in terms of temperature and pressure. And it's based on the ideal gas law. And so I think
I think let's
with
move
this
on to the
finish.
application after this. Yeah.
Yeah. So this is basically we published all of that in our working papers, um, you can still get it. There's a lot more in there and detailed discussion. But since then, we have actually been working
Michael, you
on.
put back your slide.
Yeah, we've been working on. We published some new insights into this. So, Michael, do you want to talk?
Okay,
These
first paper.
papers have been peer reviewed, and this one is in. No, go on to it. Go on.
Okay. So basically, what I'm looking at here is we have things like the Hadley cells, which are a standard sort of model that people have to explain atmospheric circulation. And now, with our new molar density way of analyzing things, we found that we can check this out. So basically, if you know the molar density and if you know the weight of the different molecules in the air, you can calculate the total amount of mass. And we can measure it. One of the things that they do in the weather balloons is they give you the speed and direction with which the air is moving at each spot where they go up through the atmosphere. And so you can calculate the mass flux. Now, the mass flux is the weight of air that's going through a square meter at any time.
Mm.
So it's a vector quantity. If you have the speed and the direction, and this is a bit technical for most people, but you can resolve a vector into east and west components. And so we can measure the total mass flux going towards the poles or towards the
Going
east or
east and
west.
west.
Right.
Okay.
So, so what we did was we took the molar the mass flux and we started analyzing that for to see what way the atmosphere
Can I
was.
just Michael, just to interrupt, just to say this graph here, what we're showing is how you can use molar density, combine the molar density. So if you know the main change in the atmospheric composition is the water content, and so if you know the water content, which is recorded by the weather balloons, and you know the wind speed, well then you can convert or you can convert the from the water vapor concentration. You can multiply the molar density. You can use that to calculate the specific density, the density of air per cubic meter, and then when
Well, you
you
see,
multiply that by
density
the
would be
speed,
the actual weighting in kilograms of the
yeah,
air. That's
then you
uh,
can actually multiply that by the or scale that by the wind speed,
what
and you can get the mass flux, which is on the bottom right hand corner.
So
You,
what we found, if you this is just for one radio sound, I'll show for a large number in a minute. But what we found is for this particular radio sound, that the if you looked at the mass, it's all going into one direction, right? As you go up, and I'll tell you the significance of this in a minute. So
Willie, if you need to leave, you can just log out and we can take
Yeah,
it.
I think you guys are in good hand. Yeah, maybe
Yeah,
I'll
okay.
go
yeah.
about
We're
10:35.
near the end. Okay, okay. That's it.
So basically, the whole business of how the atmosphere circulates and the idea behind the Hadley cells and various things like that arose out of Hadley trying in the hundreds of years ago trying to explain why the trade winds happened and so on. And so the so
It was
basically
centuries before they'd invented weather balloons.
Yeah.
yes.
Had
So
George
all
Hadley
of
come
these
in the
are,
17th century, by the way.
yeah,
Late.
all of these theories were based on ground measurements. So nobody knew what was happening as you went up through the air, except if you were going up mountains. That's the only
Yeah,
time. But
right.
the idea behind that Hadley circulation was that what happened was the air would flow in the northern hemisphere would flow from north to south. And as it was flowing that way, it heated up. And then when it reached the equator,
You're right.
it was hot enough, it started to rise up. And then Hadley didn't know about the tropopause. And
Yeah.
so about 30 or 40 years before I was born, the tropopause was discovered, and then people realized that the hot air could only get as far as the tropopause because above that the air was too hot for it to rise. And
Do you
so
want
they
to go
said,
on to the next slide and
yeah,
show the
Right,
schematic?
I
right.
just, yeah, I just showed though, but they had it going like this. So you have a circle, it traveling under the
So on the
tropopause.
graph is north to south, and then on the thing is south to north. Yeah.
So, okay. So this is the standard explanation now for the Hadley cells. So what they say is you have the sunlight here shining down and heating the ground, and the air is moving from north to south, and it's getting hotter as it comes along towards the equator. And then it rises up at the equator, and then it can't go past the tropopause because it's warmer up there. And so it then travels along under the tropopause, and as it's going north, it starts getting cold, and then it falls down, and you get this circulation pattern. And this is what is a Hadley cell. Now, there is another thing called the Brewer-Dobson behavior above the tropopause, but I won't get into that at
Yeah,
the moment.
okay, that's save that for another day because we could.
So, yes. So basically, what you're looking at is how can we use weather balloon data to check if this is true? So if you launch a weather balloon here and it goes up through the atmosphere and it's measuring the direction of the mass flux, then what you would expect if the Hadley cell was true was that the air, when you're measuring it here, you would get the air traveling in that direction. So down at ground level, it's traveling from north
Maybe
to
just to
south.
put a one short context is that don't you think it's remarkable that this concept is like a cartoon science that's been stuck into everybody's brain and computer climate models, this and that, and
I know,
essentially no one has checked this.
Yeah.
yes,
Well, you
this
couldn't
is,
without mass flux. You couldn't
yes.
That's
without
right.
mass
That's the
flux.
unique. That's the power of this molar density concept. That yeah. That's
So,
the consequence. Yes.
so
So, Michael,
Sorry.
basically, what you would say expect is as your balloon was rising up, it would the mass flux will be flowing in this direction, and then somewhere around the middle it would change over and start going north. So you'd expect the behavior to be like this. And so when we started checking with the radio sondes, we found that this wasn't the case at all. That in fact, if you look at these things here, this was where we took 5 years of data from five representative climatic regions. So we took an Arctic one, a cool temperate climate, a temperate climate, a subtropical climate, and a climate, and
sure.
a tropical climate.
Right.
And we analysed those for 5 years for these typical radiosonde things. But the one thing, for example, I'll go on to the one in Spain. I'll just magnify this up. What
Right.
we found was that instead of the
Oh, Michael, can I just explain to the audience what's been you're plotting here is the mass flux values for the average for what was it for 5 years?
5 years for
Average show,
all,
or no, this is 5 years plotting it. So
Over time.
it's
Yeah.
showing each value. What we're doing is
it's
smoothing.
been averaged over 31 points, which was
Yeah.
about
So
12.
the monthly average at each point from 2015 to 2020, and at each color represents a different
Different height,
height in the
cross
atmosphere,
section. Yeah.
and so we actually look in the
So
stratosphere.
if you looked at the ground level and then come up, this would be around where the clouds are, and going back. So around here is where the tropopause, the pressure,
And
uh,
around between the two.
the different
Like
colors. But
the
the
last
one
thing,
thing,
just to explain the graph for the audience.
yeah,
So if the value goes above the line, the positive value, that means that the north south, that the air is heading north, or is heading from the north. Is it? Yeah, it's heading to the north. If it goes above the line, and if it goes below, it's going to the south. And the thing is that all of the heights, they're all going in tandem. And
they're
so
all
They're
going.
moving up and down together at all heights.
north and
But
south together.
what it says now is instead of the atmosphere going around continuously in this Hadley circulation, the whole the convective model, as it were, the whole atmosphere is acting like a giant pendulum. So it travels in from north to south, and then after a couple of days, it comes and starts going in the opposite direction. So you can see it rocking back and forth. So what this is saying is here it's going from north to south, then it comes back down again, up again, down again. So this is saying that the whole atmosphere is moving back and forward, and it's not a
Together.
circulation pattern. So this
So
this
move
just
on to the next, and we've just wrapped things up.
so if
Yeah,
we take the average over the entire
5 minutes.
period, you can see that we don't get the back and forth or the Hadley cell
The sign
behavior.
switching, yeah, the sign switching of
yeah.
the flow of the mass flux.
What you're seeing is that the whole atmosphere, the mass flux, is going on average over the whole 5 years in this
Same
direction.
direction.
This one is in a subtropical one, and this one is in a tropical region. Now you can see you do get a change as you go up. It changes from zero and goes in the other direction.
Mauritania, just for
And
Mauritania.
the tropical thing, but and you say, right, well, that's the Hadley cell circulation model. But the problem is that it's going in the opposite direction. This is the way it should be going for the Hadley cell thing. So even though this is the only one where we found a change in the mid troposphere, it wasn't. It was going in the wrong direction. And the other thing was that the mass flux on average at the ground level wasn't equal to the total mass flux going in the other direction.
Well, I
So,
think that's kind of just give an overview. We go into a lot more detail in the actual paper, and that was
yeah,
actually just a preliminary one because we analysed 5 stations. So before we did the paper, we've
but,
analysed hundreds and hundreds all
but
around.
what this new way of analyzing the atmosphere does is it tells us that the balloon data doesn't support the various circulation cell models like the Hadley cell and that. And
And the only you can only do nobody had done that before because before they were just measuring the wind speed and they weren't measuring the mass flux. So people were just
Right, and notice
speculating.
notice that you cannot use satellite retrieval to do this. You need to measure the thing in situ, right there. That's where the balloon data comes in. Very unique, very special, and the only way that can allow a bit of a resolution of this mass flow, which is
and
very powerful. No
this,
computer model.
yeah, this paper has gone through the standard peer review process.
Yes,
So
yes.
yeah,
Yeah,
it's
so just do you want to talk briefly about our most recent papers?
Yeah, next graph, please.
Yeah,
okay. We're going to this. Okay. So what we looked at is we again used the weather balloon data to look at the tropopause, that line that
yeah.
we had moving up and down. And what we found was that the quality of data now has improved tremendously. But we found this set of data which took a reading every second as you go up through the atmosphere. They were called ozone sondes, but they measured, besides measuring water vapor and temperature and pressure, they also measured the ozone concentration. And also, they had a very accurate reading of the water vapor content all the way up to where the balloons
Hey, so
burst.
just for this thing for the audience in the paper, we look at all four. We look at and the standard WMO definition of the tropopause. We look at the ozone based and also the water vapor. But here, I think we Michael is just got to point out how
So,
the molar density is a very useful tool for calculating the tropopause.
so this is a very high resolution data set for these for a whole year in Valencia. They took very close readings, but it's just to illustrate. This is as you normally see the temperature plotted with altitude, and
All right,
what you can
I go
see.
now. Thank you, guys.
Okay, thanks, Willie.
I just leave it there, and then whatever, kick me out, kick me out. At
Yes,
least,
yeah.
at least
I don't know. You can turn the just.
my reach
Oh, yes.
appointment
Okay.
can be, my very nice. I
Your
schedule
nice
my
apartment.
beautiful, expensive appointment.
His AI generated apartment. Okay,
Okay.
thanks, Willie.
So what we're looking at here is the standard way the temperature is plotted with altitude. And what we're saying is you can also, instead of plotting the temperature versus altitude, you can plot it versus pressure. This is more useful in that it tells you the amount of air. As you can see from this, about 60% of the air is in the tropopause. But if we go on just taking that's your normal one that you see, uh,
Temperature versus altitude or height.
and this is what's called the lapse rate. So if you look at the temperature versus thing, from taking measurements on mountains and that for hundreds of years, people have known that as you go up through at different altitudes, the temperature drops off at about nearly 7 degrees per kilometer, or nearly 8 degrees per mile in Fahrenheit. And this is how, if you were to plot that with pressure, you'd see that you get a curve, a different curve for this straight line. Up until the discovery of the tropopause, people thought that this was going to go on forever like that. Um,
Onto space.
onto space. Now, what we're saying is you see the behavior with respect to temperature, but now if we look and plot instead the molar density versus the pressure, you can see with this high quality data set, you can see two clear straight lines. And again, you can see if you fit the bottom one with this, you get a very high correlation for the straight line. It's point r squared 0.999. Basically, if the r squared has a value of 1, it means that it's an absolute straight line. And so you can see this
Or
is
an
where,
absolute perfect fit to the data. It fits
yeah,
the data exactly.
yeah.
The data is a perfect sorry,
So
but
this is showing if you plot the molar density versus pressure, you could see you would get this exponential decay because the pressure drops off exponentially
I
with altitude.
I just for people that are unfamiliar with this thing, so the pressure falls off exponentially with height. So when you plot you get a straight line in against pressure. When you plot that in terms of against height, it ends up with these curves, but exponential curves. But what Michael is showing there is that the shape of the curve changes above the tropopause.
The reason I'm all just showing this is that this shows that the two forms of representing the ideal gas law work, but in a slightly different way. What we have found was that looking at these high quality ozone sondes and that sort of thing, we found that the tropopause, you could use four different variables: the temperature, the water vapor, the ozone concentration, and the molar
The
density.
water vapor
Yeah,
and the molar density.
yes,
So
and
okay,
they all give you the exact
uh,
same.
same result. But the molar density gives the cleanest, is the simplest. So that's what, in our opinion. So, okay, so I think really what we wanted to just kind of give people an overview. We obviously, there's a lot of technical stuff there, but also just to let you know what we're doing and why we think this is.
Yeah, what we're just doing in this first bit is just taking two of our dozens of papers that we put out there, and we've just looked at it, shallow look at it, but just showing how revolutionary this new approach to analyzing terms in terms of molar density and that is advancing the whole science. And it's also allowing us to check out a lot of the assumptions that had been made that nobody bothered to check. And what we find is that a lot of the assumptions are just
So we have other papers following on from that, but it's taken a long time to get these published in the peer reviewed journals. Our A lot of what we had to say was in those OPRJ papers. The peer review process is a lot lower, it's longer. It can take years to get a paper published in peer review, especially if it's going against existing paradigms, which is what this stuff is doing. But we
uh,
have those papers, and that was published in May last year. That last one, and then we have other ones that we're doing, and we can talk about
yeah,
them on the podcast
this is
when they're.
only a small fraction of the weather balloon data that we've looked at. And
Yeah,
we are using the weather balloon data just to check the assumptions in the models because these assumptions had never been checked. And what we're finding is that using these new approaches to looking at the weather balloon data, which are not new in the sense that it's old analysis, but it's applying these analyses to weather balloon data, that's what's new.
yeah.
And then that is finding that the models, assumptions in the models are not correct. They're not
So
supported by the data.
okay, so if you're still listening with us to the end, thank you for staying to the end, and uh, like and subscribe and share the video and all of that stuff. And let's wrap it up. Leave it at that for today. What do you think, Michael?
Okay.
Yeah.
Yeah, that's fine with me.
Okay.
Bye.